part. So, as always, Y is a closed-oriented three-manifold. And so let me just recall what Heegaard decomposition is. But first we say that Y has no S1 cross S2 summand if for any decomposition a connected subdecomposition of n copies of S1 cross S2 and some other three-manifold Y1, we have n equals 0. So I should mention that three-manifolds behave like numbers. They have a prime decomposition, and we just forbid one manifold to appear in the three manifolds we would like to examine. So you should think that we are like dealing with odd numbers. Number 2 is sort of excluded. So from now on, I will always assume that property, and you will see why does this property make our life a little simpler. So a Heegaard decomposition U is a collection of two handle bodies, U0 and U1, with boundary the common boundary is sigma. Of course, because of orientations, one has to be reversed, such that U0 union U1 is exactly Y. So we know what the handle body is, right? It's just, we just take a bouquet of circles in the 3 space, G circles, and we take a tubular neighborhood of that. So it's a happy fact of three-manifold topology that every three-manifold admits a Heegaard decomposition, and this is where the theory gets half of its name. So because the Floer homology runs on a Heegaard decomposition, so okay, next, so a handle body can be described by a collection of so a handle body U0 of a k simple embedded simple closed curves in sigma. We discussed that yesterday. I just repeat what the properties we require. So alpha I should be disjoint, and the dimension of the subspace spanned by the homologies of these curves in the first homology of sigma should be exactly the genus of sigma. So we will pay special attention to curve systems which provide a pair of pens decomposition of sigma. So we say sigma alpha beta is a pair of pens, Heegaard diagram, of Y if the following happens. So first of all, alpha and beta are both determine handle bodies, which in turn determine a Heegaard decomposition of Y. So determine handle bodies U0 and U1 with U0 union U1 equal to Y. So this is exactly a special case of what we discussed yesterday, but now we require them to be provide a pair of pens decomposition of sigma, and any component of sigma minus alpha. So we just take the whole surface and we delete all the alpha curves is a pair of pens. Sometimes we will discuss other decompositions where instead of pair of pens we will have 4 punctured spheres. We didn't find a good name. What is it, like a t-shirt, or what? A t-shirt decomposition. So it's just a quick remark. Every surface admits a pair of pens decomposition provided the genus of the surface is at least 2. So for the torus you can do it, for the sphere it's impossible, but for all hyperbolic surfaces there is a pair of pens decomposition. And in fact, the Heegaard diagram I produced yesterday from the double-branched cover is exactly an example of such a Heegaard diagram, where both curve systems provide a pair of pens decomposition. So why are these guys so convenient? Well, here are a few basic properties of pair of pens decompositions, but before doing that, let me just add one more definition. So sigma alpha beta pair of pens Heegaard diagram is essential if all alpha I and beta j are homologically essential. Notice that in a pair of pens decomposition you might have homologically inessential curves. Let me just give you one example. So on the genus 2 surface, I will give you 2 examples. So let's use the yellow. So if I take this to be my alpha 1, and this is my alpha 2, and this is alpha 3, then obviously this is a pair of pens decomposition. I just cut it into 2 pieces, and you see the 2 pairs of pens, and these are all homologically essential curves, as for example proved by these dual curves which intersect them once here and there. As opposed to this decomposition, where we still have 2 pair of pens, but this curve is homologically inessential. It's the boundary of this subsurface. So from now on, we will always assume that the pair of pens decompositions are homologically essential. And so here are a few properties, a few lemmas, which sort of justify why we do that. So here is lemma 1. If Y has no S1 cross S2 summoned, and sigma alpha beta is an essential pair of pens decomposition, pair of pens Heegaard diagram, then for every alpha I, there is a beta j such that alpha I intersection beta j is not empty. So if we have an essential pair of pens decomposition of an odd 3-manifold, then all the alphas are intersected by betas. Okay, so why is that? So here is. So I will sort of provide sketches of proofs. These are not very deep statements. It's just to get into shape. So what if there is? So suppose there is an alpha I such that it is disjoint from all beta j. Then consider the beta pair of pens decomposition. It should be in one of the pair of pens. But being in a pair of pens is actually a very convenient thing. So here is the pair of pens my alpha j is. So in a pair of pens, there is only one way you can be in, namely you have to be parallel with one of the boundary components. So this would mean that there is a beta j such that alpha I and beta j are parallel. But that's a problem. Why is it a problem? So both are homologically essential curves on the surface, and so how do we create our 3-manifold? We just add two handles, 3-dimensional two handles along alphas and the betas, right? So when we just add so here is my sigma. When I add the two handle along alpha, I create a half disk, and when I add the two handle along beta, I create another half disk. So altogether, I get a homologically essential S1 cross S2, which will just produce an S1 cross S2 summoned in the 3-manifold, which is forbidden. So somehow, it's impossible that there are these joint alpha and beta curves. Or it's impossible to have an alpha curve which is disjoint from all the betas. Okay.
So where did you use this essentialness of this pair of pens in this proof?
That these are homologically essential. So somehow, here is the. So you can create the S2, but the S2 is a homologically essential S2 because being homologically essential, there is an S1 in sigma which intersects it in one point, a circle which intersects, and that provides you the S1 direction in the S1 cross S2. Okay, so why are we happy about this property? We are not happy yet, but so here is lemma 2. So now I will always assume these two properties, that my pair of pens decomposition is an essential pair of pens decomposition, and Y doesn't contain an S1 cross S2 because I always want to use this property. And so the next statement is that sigma alpha beta admits a unique Bygone-free model. So I will not prove this, but let me just explain it a little better, i.e. there is an essential pair of pens decomposition, Heegaard diagram, sigma alpha prime beta prime, such that alpha prime is isotopic to alpha, beta prime is isotopic to beta, and in sigma alpha prime beta prime there are no bygones. So this means a bygone-free model. And if we start with such a decomposition, then this is essentially unique. Meaning that if you find two different, then there is a homeomorphism of the surface which brings one into the other. Somehow we have to develop this feeling that to transform one alpha into another alpha prime is sort of easy. To do it with the betas is also easy. The problem is when you want to do it for both. And the whole theory of like this Heegaard-Floer theory measures how the alphas and the betas intersect each other. If you have only one such system, either the alpha or the beta curves, you can always normalize it. But somehow the difference between the two is exactly the mapping class group element which glues together the two handle bodies. So, well, the theorem is actually not very deep. So what you do is you just give an algorithm to create a bigone free model. How do you do that? Well, whenever you see a bigone, you get rid of it. You know, this is the depth. You know, it's brute force. So if you see a bigone, something like that, then actually you can always assume that you only isotope, say, the beta curves. Then you just turn it into like this. And since there are finitely many intersection points, so it's sort of not wise to do an induction based on the number of bigones, because it might happen that somehow you didn't reduce the number of bigones. You just made this move, and something which was not a bigone before, it was a rectangle, now became a bigone. Right? But you see that the number of intersection points decreased, and so by induction it will stop at some point, and you have to argue that it will be always the same decomposition, and the argument is again not very hard, and I will not give the complete details. Yep. Yeah, but so, you know, it depends on what do you want to do. So at the end of the day, we would like to say that you give me whichever pair of pants diagram you want. We produce some chain complex, and the homology of the chain complex should be isomorphic for all choices, right? So, you know, we will make certain choices, and you propose to make a choice of a hyperbolic metric, and, you know, then you have to get rid of that choice. So, okay, just bear with me. Okay, so I just want to argue that it doesn't matter how you do this algorithm, you will always get the same thing. Of course, you know, you're just in front of a huge pair of pants diagram with full of bigones, and so you just have to tell me which bigones to cancel in which order, and of course, either the two bigones have nothing to do with each other, where you start the algorithm and then the order doesn't matter, or they are next to each other, something like this. And then when you cancel this one and then that one, you have to argue that they will get the same answer, and you will. And the only problem could appear when you have two bigones like this, and then first you move this one to the other side, or you move the blue inside, this will, or the blue outside, it will give you two different diagrams. But this is exactly the case when you have, after isotopy, you will have two disjoint, two parallel circles, and that's forbidden. Okay, so again, so we have to keep in mind exactly what Ko was raising. So, you know, we will make certain choices, and we have to make sure that at the end of the day, the chain complex what we will get is independent of these choices. So this is very convenient, because here, starting from something, there is a unique way to get to the next step. So we don't have to prove anything. Okay. And so now, what do we do next? Well, of course, we would like to have a Heegaard diagram in which the Floer homology is simple. We don't have to use any holomorphic considerations, and these are the nice diagrams. So how to turn a pair of pants, such an essential pair of pants diagram into nice. So let's examine the domains in a bigon-free pair of pants diagram. So suppose sigma alpha beta is an essential bigon-free pair of pens Heegaard diagram. So what are the domains? How can we understand? Well, let's take an alpha pair of pens. Well, I will use this color code. So so this is P alpha pair of pens. So it's just a subsurface bounded by 3 alpha curves. So how do the beta curves look like in this segment? So I just take the intersection of P with all the beta curves. Well, let's take one single beta curve. How does it look like? Well, it cannot be something like that because it's a bigone-free diagram, so that's forbidden. So it has 2 choices. Either it connects 2 different boundary circles, so it goes like this, say, or it cuts back to the same boundary, something like that, right? Of course, it could go around, it could do something like, I don't know, something like this. You apply the mapping class group of the pair of pens to it, but after an appropriate diffeomorphism.
I don't have it. What are you doing right now?
So, okay, so consider so you just take a beta curve and intersect it with P, and I would like to convince you that there are like 2 possibilities. Up to diffeomorphism, it looks either like this or like that.
You might have lots of components.
Say it again?
Each component.
Yeah, so one component.
It probably comes in 1,000 times.
Yeah. So we start with one component. These are the 2 possibilities up to diffeomorphism of the pair of pens. Now we just, okay, so we agree on that. So it either connects 2 different or cuts back to the same. Okay, so the next step is now consider all the betas intersecting P and all components. I claim that there are like 3 fundamentally different situations, and these are these. So it can happen that we have something like that, or this. So of course the number of strands is irrelevant. So there are plenty of them, maybe 1. Notice that it's impossible to have a circle without a red circle without a blue intersecting it. We just agreed on that every alpha curve is intersected by some beta. So there should be some curve which intersects this circle, and there should be some curve which intersects that one, and there should be some which intersects the outer one. And then you just examine, and this is all we can have. So from now on, the bunch of parallel curves will be denoted by one single blue. So there are these 3 possibilities. What are the domains? So you remember, we are concerned about the domains This is what I call the elementary domains, and remember, a nice diagram means that these are either rectangles or bigones or contain base points. I didn't put any base points yet, now we will, but notice first that in a bigone-free essential pair of pens diagram there are only rectangles, hexagons, and octagons, as we can see. So every elementary domain is in one of the alpha pair of pens, so it's either here or there or there. This is a rectangle, This is a rectangle. These are all rectangles. This is an octagon. This is a hexagon, 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 hexagon. Right? So just, we just count 1, 2, 3, 4, 5, 6, and so on. So it's pretty close, but it's not good enough. What's the problem? So now we are planning to put down base points. What's the rule? So let me just remind you. Every component of sigma minus alpha is allowed or must contain a unique base point. And the same holds for every beta, for every component of sigma minus beta. So when we are in this situation, we just put a base point there. And that's good. So our secret plan is to sort of occupy all the domains which are not rectangles or bigons with base points, and then we get a nice diagram. First of all, we don't see bigons yet, which is sort of comforting, but there is a little problem. So in this component, in this alpha component, there are 2 hexagons. So what do we do? Like half a base point here, half a base point there? That doesn't work. So we can put down 2 base points, but then I would violate my own rule. But there is a way out, because we are always allowed to add more curves. So what we'll do is, in this case, so this is fine. In this case, I will add 1 curve. So from now on, instead of drawing all these parallel curves, I will just symbolize them by 1 single straight beta. And so I add the following curve. I will sort of draw it with dashed. Notice that this dashed line separates the 2 base points. So now the 2 base points are in different alpha components. And let's see how do the domains look like. So this is still 1, 2, 3, 4, 5, 6. This is still a 6gon. This is a rectangle. This is a rectangle. This outer guy is also a rectangle. There is another 6gon. 1, 2, 3, 4, 5, 6, 7, 8. That's an 8gon. And there is a bigon. So locally everything is fine. And we just do it for every alpha component. Go. Say it again.
You need a new beta for that to go with that one?
Yeah, so first we do it for the alphas, and then we'll do it for the betas. But let me just take care of this guy. So in this case, we do what we did before. We just put 2 base points, and then to satisfy this condition, we have to add 1 alpha curve, and we add this guy. And again, a little check shows that now it's fine. Every domain which is not a bigon or a rectangle actually admits a base point. Now I added lots of alpha curves. I have to add the same amount of beta curves, but luckily there are an equal number of octagons when you view it from the alpha or from the beta perspective, because an octagon is an octagon, no matter how you look at it. So there are certain alpha pair of pens which contain an octagon where we didn't do anything. These same octagons sit in a beta pair of pens, and these guys may be with different friends, right? They are friends in the alpha perspective. They are in the same alpha pair of pens, but this guy will have another hexagon when you view it in the beta pair of pens decomposition. So you just add the similar beta curves, and what we get, so from this, get a nice Heegaard diagram for y. Okay, so we start with a random pair of pens decomposition. we make it Beighton free by isotopies, and then we add extra curves when necessary. It might happen that all guys are, these two models don't show up. Everybody is an octagon. And then we don't have to do anything. In fact, the Heegaard diagram I was producing yesterday with the double-branched cover has this property that no such situation happens, and it's only octagons, and it was nice to start with. But in general, that's too much of a restriction. I was sort of indicating that what we would like to do is sort of loosen a little bit that very strong condition, or that very rigid construction, and this is what happens.
Why this thing for the adding first with the alpha and then the beta will interfere with each other?
Well, that's a good question, and one has to think a little bit that whether it ruins the niceness, right? And so, well, you know, you can just forget about this. So the Beigons are there, but we always think of the Beigons are being very narrow and go almost all the way to the base point. And it just, you want me to give the, they don't. Okay, so what happens? So start with a pair of pens, essential pair of pens, Heegaard diagram. Then make it Beighton free, and I will denote it by the same letters, and then what else do we do? Okay. And then add the further alpha and beta curves and call it sigma alpha completed, beta completed, and this is now a nice diagram. And Co is right, we have to check that the result is nice. First you add the alpha curves, and then you add the beta curves, and you have to convince yourself that in fact the result will be nice. It needs a little checking, but it's not very complicated. You just have to check what happens with the 6-gon, and with both transitions, and then it might develop some Beigons, but still there is a base point in the middle, so it doesn't matter. Okay, so now what we would like to do, what I will do tomorrow or whenever, I don't know when, in my last lecture, we will produce a chain complex from this diagram. Sorry, and we also chose base points. So we have, in fact, sigma alpha completed, beta completed, and all these W's. Right? I just drew the base points here. And so having this information, we will produce combinatorially a chain complex from which we get the Heegaard Floer homology group. And all we have to prove is that none of these choices actually change the resulting Floer homology, so that it's independent of these choices. Well, this is an extremely convenient step.
Why that the combinatorial Floer homology is isomorphic to Heegaard Floer homology?
Why is that?
Yeah.
Well, I will talk about that when I define the chain complex. But yeah, okay, let's save that. It's the Riemann mapping theorem, in fact. But we will get to that when I define the chain complex. But now I would like to show you, what goes into proving the independence of choices. So what we would like to need is sort of, if we have two different choices in any of these steps, we should be able to connect the resulting chain complexes. And in order to do that, we should be able to connect the resulting diagrams. And so here are 3 moves, 4, which we'll show to be convenient in our discussion. Yeah, let me just. So here is the definition first. Sigma alpha beta W is called a convenient diagram if it is the result of this algorithm. So if you can present sigma alpha beta W by starting with a pair of pens, essential pair of pens Heegaard diagram, and you do all these modifications and you get what you prescribe, then you call it a convenient Heegaard diagram. So in particular, every convenient diagram is nice. I know it's sort of hard. I mean, nice is already taken. So what do you say? Beautiful or gorgeous or something? Okay. Very nice. And then you prove that very nice is in fact nice. No? So here are 4 moves. 4 nice moves. 1. Nice isotopy. So how do we define an isotopy? What's the convenient way to define an isotopy of curves on sigma? So suppose that gamma is an arc in sigma with the following properties. So gamma naught is in some alpha I, and gamma minus gamma naught is disjoint from alpha. So in other words, gamma starts on an alpha curve and then it becomes disjoint from the alpha curves. Gamma 1 is in a domain, an elementary domain, which is either a bigone or a domain with a point. And what else? Gamma is transversal to all the betas, and 2 more, one simple and one less simple property, but maybe it's better if I draw. So there are a few curves, something like that. So I want to prescribe a curve gamma with the property that it starts on an alpha curve, then it stays disjoint from the alphas, but it might intersect the betas, and it stops in the middle of a domain. So isotopy is just moving the curves, and this gamma will help me to apply a finger move, right? I will just push my finger along gamma and modify this single alpha curve on which gamma starts. Jungen?
So I thought you're supposed to not have this homologically.
Well, yeah, I knew that it will confuse you, but of course now I changed everything, right? So I added these curves, and they might be homologically trivial, but this is just a. What should I do? So here is this gamma curve. So it starts on an alpha, then it stays disjoint from the alphas, it's transverse to the betas, it will end up in a domain. We require that this domain is either a bigone or a domain with a W. There is this domain behind the point. So the domain which contains the starting point on its boundary, but the gamma starts in the other direction. So this is what I will call D gamma 0. So this is D gamma 0. Has the same property as the endpoint. It's either a bigone or is a bigone or contains a point. And the final property is here, and I will draw again. So suppose we have a domain something like that, and then gamma comes in, goes out, it sort of does like this and like that. We just take for every domain D minus gamma. It will have various components, and we allow only one component to be different from a bigone or rectangle, and if there is such a domain, it should contain a base point. Can have at most one component which is not bigone and rectangle, and such component contains W. Okay, so you have this surface, lots of alpha and beta curves, lots of W's all over the place in every component, and then there are these nice curves which start on an alpha, stay disjoint from the alphas, intersect the betas transversely. There is a restriction on how they start and how they arrive, and whenever they cut across a domain, they should do it in a nice manner, that either it partitions only to bigones and rectangles, or if there is a domain which is more complicated, this is because there is a base point. So for example, this is forbidden. That there is this domain and there is no base point, and my stupid gamma comes in and then leaves immediately. Then this component is a sixgone, but it doesn't have a base point, so we don't allow that. Whenever we have such a curve, it induces an isotopy of the alpha on which it resides, and this is called a nice isotopy. So a nice isotopy is always induced by such a gamma. So let me just write it down. Such a gamma induces an isotopy of alpha I, which contains gamma naught, and this is called a nice isotopy. Okay, so this is move number one. And you are allowed to do that. The property is that if you start with a nice diagram and you apply a nice isotopy, the result will be nice. You never sort of screw it up. Step number 2, nice handle slide. That's much simpler. So what is a handle slide? Well, in order to make a handle slide, you need two curves of the same type, say 2 alpha curves. Of course, needless to say, you have to allow nice beta isotopies, so similar properties of gammas where they start on a beta curve, they stay disjoint from the betas, and they transversely intersect the alphas. What's a handle slide? Well, the handle slide is more restrictive. So what is a handle slide to start with? So handle slide can be performed on 2 curves of the same type, either 2 alpha curves or 2 beta curves. And the strategy is that we just take a parallel copy of one of them, we just displace it a little bit, and then we take a connected sum. And so we forget about the alpha curve and we replace it with the connected sum curve, which is now this. So David will talk about the handle slides. You will, right?
Yeah,
on Thursday. So, you know.
Only graduate students, so you're not a graduate student.
Then you will never know. But most probably you know what the handle slide is. I'm just sort of giving a pictorial description of handle slides in this context. So these are allowed provided, so again, what do we need? In order to specify a handle slide, we have to connect my alpha curve and my beta, my alpha 1 and my alpha 2. So in order to specify, we need to tell this path connecting the two curves which participate in the handle slide. And so in order to prescribe a nice handle slide, I should pose some condition on that delta curve, right? And so here are the conditions. So the curve delta must be in an elementary rectangle. So the only possibility, it should be in a rectangle where no other alpha and beta curves are, plus, so here is delta 0 and this is delta 1. So delta 0 indicates the curve which we will handle slide over the other one, which is indicated by delta 1. And so again, there is this domain d delta 0, which is behind the point where the arc starts, and d delta 0 must contain a base point, a point W. And again, the reason for that is that we would like to keep the result of a nice handle slide to be nice if we start with a nice diagram. So notice that, you know, this is sort of an important requirement. Notice that, say, we don't obey that. And the domain behind the delta naught is a rectangle. So it was a nice diagram, rectangles are allowed, and the d delta 0 is a rectangle. Then I claim that we'll run into trouble. Because what happens with the nice handle slide? Well, we just create this new diagram, and suddenly the rectangle opened up, and it became a sixagon, right? No, an octagon, right? 1, 2, 3, 4 red, 1, 2, whoops. 1, 2, 3, 4 blue, so it has 8 sides. And that's too bad unless it has a base point. But how can it gain a base point? It had to have a base point to start with. So we just required that, and in fact it's not very hard to see that this is the only thing which can go wrong. We created these two bigons and some rectangles here. Okay, so this is nice in a sense that it turns a nice diagram into a nice diagram. So these are two moves, and there are two further ones. So so the third is a nice type G stabilization. So these will be simple. So suppose that D is a domain containing a base point. So it looks like this. You see, whenever I put a base point, I sort of draw a polygon with many sides, but it's not necessary. Bigons can have base points and rectangles can have base points. The only thing which is not allowed, that there is a polygon with lots of sides and it doesn't have a base point. And so a type G stabilization is just connect some with a torus and add an alpha and the beta curve. So the domain will not be simply connected anymore. Of course, I didn't require this to be simply connected to start with. And but notice that nothing really changed. I mean, the combinatorial description of the domains did not change at all outside of this domain D. And in D, there is a base point anyhow, so we don't care how it looks. So again, this nice types G stabilization, because we perform it at the domain which contains a base point, it doesn't change niceness. If it was nice before, it's nice. If it wasn't nice before, then we don't care anyhow. And then there is the last step. Number 4, type B stabilization. Again, suppose that D contains a base point. So and so here is the base point. And now we don't increase the genus of the Heegaard surface. Notice that here, this little, I don't know how clear this is, but I tried to connect something with the torus. So we increase the genus, and we also increase the number of alpha and beta curves, but we didn't change the number of base points. Now we don't touch the surface, we don't increase its genus, but we add an alpha and a beta curve, and we add the base point. And this is the rule. We did that yesterday, right? Now the new thing is that I require this to happen inside a domain which contains a base point. Notice that in the result there will be a base point in the bigone. It's okay. But there is no other domain which is not a bigone and the rectangle which can get away without having a base point. And also this D picked up some interesting topology, which is again fine. Okay, so here are 4 moves. And so here's the theorem which we would like to prove. Well, a definition first. So suppose sigma 1, alpha 1, beta 1, and sigma 2, alpha 2, beta 2, well, there are the W's. Diagrams of Y, of the 3-manifold Y, are nicely connected so let's call it D1, and this is D2, diagram 1 and diagram 2, if there is a sequence D upper 1, D up 2, Dn of diagrams such that my starting diagram is exactly the starting of the sequence, and the second one is the end of the sequence, and di and di plus 1 differ by a nice move.
In one direction or the other.
In one direction or the other. So either you apply a nice isotopy on D1, Di, or you apply a nice isotopy on Di plus 1, and so on. So, you know, this is just to spare introducing nice destabilizations. We don't care.
What's sort of striking to me is a handle slide. Normally, a handle slide, you can do another handle slide to undo it. But it looks like your nice handle slide, you have to like
There is a direction.
There's handle slide to undo it. You can't undo it with a nice handle slide.
Yeah, but you allow, so there is no direction, right? And then, you can nice handle slide up, down, so there is this zigzag. So we say that two diagrams are nicely connected if, with a sequence of nice moves, one can be transformed into the other. Okay, so far so good. So here is the theorem. Well, there are two parts of the theorem. One I will state today, and then we'll discuss the second part on Friday, and I will just sort of indicate what the statement will be. Well, I mean, you don't have to. I mean, if they are not nice, then these guys will not be nice. If they happen to be nice. So this concept makes sense. It doesn't matter. Yeah, so here is the theorem. So part one, this is what I would like to indicate very briefly today, and then the part two will be indicated very briefly on Friday. So if D1 and D2 are two convenient diagrams for Y, again, remember Y is a three-manifold which doesn't have S1 cross S2 summands, then D1 and D2 are nicely connected. So this is what I would like to indicate in the next 10 minutes. And then part two, so let's call it like part one. Part two, I don't make an exact statement, but I just don't want you to lose perspective. So the Heegaard Floer homology does not change under nice moves. Of course, I didn't define Heegaard Floer homology yet, but whatever we will do, it would better respect nice moves, and then we have a well-defined theory, right? So it sort of makes life a little easy because we have only 4 moves to check. This is a little harder, and let me just give you sort of a diagrammatic explanation. So this potato is supposed to indicate all Heegaard diagrams of Y. So all Heegaard diagrams. There is this very little sub-potato. These are the Heegaard diagrams I constructed yesterday, coming from the branched cover construction. These are nice, so these are the coming from the branched cover. Those are automatically convenient because you don't have to make any further choices. So the convenient diagrams comprise a slightly larger subpotato. So these are the convenient diagrams. All convenient diagrams are nice. So nice diagrams are even larger, a little bit. So these are the nice. You give a name for the rest. Those are the ugly guys. Yeah, we don't like them. So what is the statement here? It says that if you take 2 convenient diagrams, then there is a sequence when we only perform nice moves, so they are nicely connected, meaning that there is a sequence where we perform only nice moves, which keeps niceness, which connects one to the other. So the sequence, of course, can leave the word of convenient diagrams, but it can never leave the word of nice diagrams. Now, of course, it's a question whether we sweep out all nice diagrams or we don't, and we don't know the answer for that. So somehow, this is sort of a nice and easy set, but it's not sort of convex for this kind of moves. You might need to leave it, but luckily the Heegaard-Floer homology groups will be defined for nice diagrams without any respect of whether the nice diagram happens to be convenient or not. But the convenient property is convenient because you can connect them by these moves. If you give me two nice diagrams, I don't know whether you can connect them with these four moves. So this is where, when you do this, when you create this path, this will be the point where somehow those properties we discussed, the Beigen-free model, the uniqueness of the Beigen-free model, and the whole construction will become sort of handy. Okay? So let me just indicate how to prove number one. Important choice, and this is the hardest to get rid of. Then we take the Beigen-free model, and then we take the completion. Add new alpha and beta curves and W to turn it into a nice diagram. Right? So this is what we have to check, that at every choice we made has no effect on the Floer homology, and the way we will do it is to show that every choice can be connected by nice moves. So of course, I was planning to go through all these steps, but I won't do that.
I thought there were no choices anywhere there. I thought there were no choices in those arrows. Beigen
Oh, yeah.
Unique, right? Beigen-free was unique.
This is unique.
No choice there.
Okay, so how about...
One was just...
No. I mean, let me just spend... Well, I spend 1 minute on this, and then the rest of the time in this arrow. So here there are two choices. So first you have to tell me which Heegaard decomposition you take. So choices. Heegaard decomposition, U or U prime, and then there is this fundamental theorem of Reidemeister and Singer, who describes when two Heegaard decompositions describe the same three-manifold, namely the only thing you can do is to stabilize them. Connect some with the Heegaard decomposition of S3, the toroidal Heegaard decomposition. So that's one choice, and the other choice is these alpha and beta essential pair of pairs. So this is Reidemeister-Singer, and then the choice of alpha and beta, well, they are completely independent. So you have the Heegaard decomposition, and you have to choose a pair of pairs for one and a pair of pairs for the other. So we can just deal with two different choices in one side. And so here is a theorem of Feng Luo saying that if you have two pair of pairs decomposition giving the same handle body, so alpha and alpha prime give the same handle body U naught, then they can be connected by a sequence of flips. By a sequence of flips, where this is a flip. So a flip takes place on a t-shirt. It doesn't look like a t-shirt, but it is. You just have to bend a little bit. And so the flip is that this was your original choice, and now you choose it. Now you change it to this one. Okay? So the statement is that if you have two different pair of pairs decomposition, then applying this finitely many times, you can transform one into the other. Of course, well, so first of all, it's not important, because I always pursued an essential, but in fact what we used in the proof is that one of them is essential. So you start with an essential, and then you keep always the beta to be essential, and then you just transform the alpha. But in fact, Luo's result says that you can do it in a way that in every step it stays essential. They even have a name for it. They call it markings, essential pair of pants decompositions, and these are like studied objects. So you can do it in a t-shirt where everybody stays essential. It's not obvious.
This is essential, right?
Say it again?
The curve is essential.
Well, the statement is that you can choose the t-shirt such that this is essential and this will be essential as well. This being essential doesn't imply that this is essential. In a pair of pants, essential means that the two other guys are not the same curves, right? So these are not glued together, otherwise this wouldn't be essential, but this would. But the theorem of Luo says that you can do it.
Oh, right.
Okay? Okay, so, well, that's sort of, this is the hardest part, because it sort of changes the curve system very deep, before all these other choices are made. So when you change it, then lots of changes should be applied, and that's one problem. The other problem is that, you remember, the pair of pants doesn't have a very serious mapping class group. Everybody is parallel to the boundary. The t-shirt is much more complicated. There are all kinds of crazy curves, and either we normalize according to this curve, or we normalize its picture according to the beta curves which are in there, but we can't do it parallel. And so this is why it needs a serious argument. And this is actually the game I was sort of referring to, like you take a surface and you have lots of curves and then you just play with the curves.
But Heegaard did that, right? Heegaard did that kind of stuff.
Yeah, so but they were lazy enough not to do it in that context, so we had to do that. It's a very sad thing that people didn't think ahead and they had no intention to be nice for Heegaard homology. But they had some very nice results, for example, regarding this Beigen-free story. But let me just indicate how the last step works. Okay, so this is quite a long story, so we are not talking. How much time do I have? 2 minutes. More than enough. Okay. So let me just give you an idea what kind of problems we can have. So maybe I will just pick a simple case. So although David was sort of suggesting that we don't have choices here, but we do. For example, so here are the two W's. And I add my new curve, and this is what I propose to add. Right? But I have no good reason why I picked it in this way and not upside down. Not to mention that somehow this curve, this blue arc is distinguished. It intersects it twice, and this once and this once. But I could draw another figure when this is intersected twice. So maybe I will do that. And so it goes like this. So it's not unique. It depends on how you presented this pair of pants, and there are a couple of choices. Again, I can turn it upside down, or I can select this as my distinguished curve. And so we all have to connect them. And so what I will do now, I will connect this one and that one. Okay, so there are the W's. So I will just show a sequence of nice moves which transforms this into that. Okay, so the first move is that I will do a handle slide here, which is okay, because what do we need for a nice handle slide? It should happen in a rectangle, which is in a rectangle, and it should be backed up by a base point. And the base point, you can just move it within its domain, so it's just right behind and giving support. So what's the result of the handle slide? Now I will stop doing this dashed line. I will just draw the line. So it will look like this. Like that, right? So it's somehow you have to be careful when you do handle slides in curvy calculus. Then the isotopy class of the curve is not so important. The isotopy class is important, but the actual shape of the curve is not important. But now we have to be very careful and keep it in the shape I drew. Okay, here is W, and now you should see that now applying a nice isotopy on that curve, namely grabbing this point, which is backed up by a base point, and pulling it here, which is a domain containing a base point, we get this. So it will look like this. And luckily these two pictures are the same. So, a nice handle slide here and a nice isotopy here. You cannot isotope this one back somehow. If you isotope this like that, then it won't do it, right? It will just give two horns coming in. So somehow you have to do the isotopy from here to there. But so this shows that these two choices are the same, and the similar argument shows that all the choices are the same. So you can get rid of dependence here. That's actually a pretty short proof. And to get independence of this step, that requires a little more thought. And I think we'll not go into the details. Pleasant as they are, we'll just skip that today. And so the plan is for Friday is that I give you the Floer homology groups, and all we have to do is to check that, so they will be defined for nice diagrams, and all we have to check that nice moves don't change those groups. Okay.